Okay, in this second video, we're going to look at some equations, radioactive decay equations. We're getting on to the proper A-level stuff. This is an unstable nucleus of a particular isotope, a radioisotope, and at some point in the future it will decay. It is unstable. We can't predict when it will decay because the process is random. It's a bit like rolling a dice. You can't predict when you'll roll a 6. You might roll one straight away. You might do 100 throws and not roll a 6. What we can say is that the probability that it will decay in a certain time, for example in the next second, and we call that the decay constant. It's quite a common question. What is meant by the decay constant? It's the probability that a nucleus will decay in a certain time. And we use the symbol lambda, and it's measured in seconds to the -1, the decay constant. A sample of this isotope will contain a very large number of unstable nuclei. Capital N is the number at any time. In a particular time, half of the nuclei will decay, and that time is called the half-life. The half-life is also the time over which there's a 50-50 chance that a particular nucleus will decay. The daughter nuclei, what you're left with, may or may not be stable, but we'll assume that they are for simplicity. The number of nuclei remaining will fall exponentially with time. Look at the graph. This is an exponential decay, and the number of decays per second will also fall exponentially, and the number of decays per second is called the activity of the sample. So the activity of the sample falls exponentially with time. Here are some important equations which you must learn. dN dt is the activity, the rate of change of n, and that equals minus lambda n. T half is the half-life, and that's equal to log 2 over lambda. So lambda is equal to log 2 over the half-life. And then n equals n naught e to the minus lambda t. N naught is what you start with. N is the value of n at any particular time. To determine the half-life of an isotope, you take measurements of background radiation because you don't want them getting in the way, so you subtract that from all of your readings. You measure the amount of radiation emitted by a sample in equal amounts of time. You plot a graph of that against time, and from the graph you find out how long it takes for the count rate to halve. You do that 2 or 3 different places on the graph, and you take an average, and that's how you find the half-life. Note that when you're measuring with your GM tube, you're not measuring the activity, because all of the decays that take place aren't going to produce particles that you detect. You'll just detect a very small fraction of the particles. So we're not calling that the activity, I'm just calling that the count rate. Here's an example of a sum that you should be able to do. Have a read of it. Pause the video, have a go, see if you can work it out yourself. And there's the answer. And here's another sum for you to do. Have a read of it, pause the video, work it out. Notice on this one there's a little trick. Very often the amount of time involved is a multiple of half-lives, and keep an eye out for that. It could save you a bit of time.